All right, we are moving into Chapter 7 now, and that brings us to the idea of energy, and we are going to discuss today electric potential energy. That's going to allow us to talk next class about the quantity known as the electric potential or voltage. All right, so a little reminder, in 101, let me zoom in here, in 101, we talked about gravitational potential energy, and this picture here kind of sums up the idea. This person is holding an apple in picture 1. In picture 2, they have released the apple, and so initially the apple is at rest, and in picture 2, the apple is falling towards the ground. It is now moving, and so in the first picture, the apple has no kinetic energy associated with it, but in picture 2, there is kinetic energy. And so the question is, well, where does that energy come from? And that brings us to the idea of potential energy. And since the force that's doing work in this example is gravity, then this is known as gravitational potential energy. And if you remember, back to 101, our definition for work is the dot product of the force being applied dotted into the path that the object is traveling, and then that's integrated from the starting point to the ending point. And so something analogous happens in related to the electric force. So here I've got my picture 1. I've got a person holding a charge, big Q, near a charge, little q, and this little q, that blue highlight I'm using to say that that charge is fixed, right? It's permanently placed over there on the left. So in picture 1, our movable charge is at rest, and then in picture 2, the person's picked up their foot, and the charge is now moving off to the right. So picture 1, no kinetic energy. Picture 2, now there is kinetic energy. Where did that energy come from? That energy came from electric potential energy. And so remember, for electric phenomena, the force that we're talking about is the Coulomb force. That's K, Q1, Q2 over R squared, and the force is always in the direction along the line that connects the two charges. So, zoom out a little bit. So our definition for work right here, we've got our Coulomb force dotted into dl, so that's, in this example, R is pointing along this line. And so R1 in the first picture, R2 in the second picture. And so those directions are the direction of the force and the path is the same, and so that dot product just turns into the product. And then we take the integral or the antiderivative, and then we just rearrange the terms, and we end up with this expression all the way over here. We've got a negative sign out front, and then we've got the difference between k QQ over R2 minus k QQ over R1. And so we can recognize immediately from the work energy theorem in 101 that, well, if we have a force doing work, then that's the work done is equal to the change in the kinetic energy, but it's also equal to the negative of the change in the potential energy. And so what that means is that this term right here must be the change in the potential energy. So that allows us to define, right, so that's what I've got written here. And so that allows us to identify or define the potential energy due to electric charges or associated with electric charges. And so here is our potential energy expression. So 2-point charges separated at a distance r, the potential energy is given by this. Note that the charge type is used as an algebraic sign in this expression. 2 positive charges or 2 negative charges, the potential energy between those 2 charges will be positive. And a positive and a negative charge, the potential energy will be negative. Now, just like in 101, potential energy is arbitrary, it's position-based, and so you have to set a 0 point. And for electric potential energy, the expression here that we're using is defined so that the potential energy between 2-point charges is 0 when the 2 charges are infinitely far apart, when r equals infinity. Right? In 101, oftentimes what we would say is that the gravitational potential energy is 0 a lot of times at the ground. Right? We would set the lowest height in the problem as potential energy 0 and then go from there. The last thing I want to mention is that since the electric force is conservative, that means if you go around a closed path, the integral has to be 0. Right? It doesn't matter how you get from point A to point B, and if point A and point B are the same location, like if I went around this over here, if you end up at the same place that you started, that path integral is 0. That means that there's no work that's been done by the electrostatic force. So, since our electric force is related to the electric field, that also means that if you go around a closed path with E dot dl, then that is also 0. All right, so now I'm going to work through an example, and so I'm going to find how much work is needed to assemble the charge configuration here in this picture. This is one of the example problems in the book, so right now, pause the video, give this a shot on your own, come back, unpause, and watch how we work on this. Okay, so how much work is needed to assemble this charge configuration? Well, first off, we're going to start with all of the charges infinitely far apart. And so we're going to essentially clean out a region of space where there is no charge at all. And so I'm going to start with all the charges infinitely far away from each other. So essentially the potential energy of that configuration is 0. And I want to ask how much work is it going to take to bring in the first charge. And the first one I'm going to bring in is the 5 microcoulomb charge. Doesn't matter which one you choose. Well, the answer is it doesn't take any work to do that because there's no electric field in this region because there are no other charges. So the first charge comes in for free, right? It takes no work to do that. But the next question, how much work to bring in the next charge? And the next one I'm going to bring in is the 2 microcoulomb. Again, the order doesn't matter. Now, notice I've put the blue highlight around the 5 microcoulomb. I've brought that in and I've put a pin in it, right? It's stuck there, so it's permanent now. Remember, electrostatics, the source charges are not permitted to move. So I bring in from infinity this 2 microcoulomb charge, right? And I place it right there, 1 centimeter away. Well, how much work did that take? We just go back to the definition of work, and we just plug in the values, and I get out plus 9 joules. It took 9 joules for me to bring that 2 microcoulomb charge from infinitely far away to 1 centimeter away. All right, cool. Now I want to bring in the next charge. Let's bring in the 4 microcoulomb charge, this one up here. All right, so now I've got 2 charges that are permanently fixed, and I want to bring in this 4 microcoulomb charge. All right, well that means now I'm going to have to do 2 calculations. I'm going to have to figure out the work required to bring in the 4 microcoulomb charge with a 5 microcoulomb charge in the space, but also how much work to bring it in if there's a 2 microcoulomb charge. And so again, I do the exact same calculation for each. Notice that R is different, and that's because the 2 microcoulomb charge is on the diagonal, right? And so I do that calculation, and I get 18 joules, and I get 5.1 joules. And so now I've got 3 charges, and I want to bring in the last charge, the 3 microcoulomb, and you'll notice now I've got all 3 of the source charges fixed. And so I bring in this last charge from infinitely far away. And so now I've got to do 3 calculations. And again, I've got 3 source charges in the space, so I've got to do 3 calculations. Again, pay attention to the separations. I'm 1 centimeter away from 2 of the charges, but I'm 1.4 centimeters away from the third one. And so I do that calculation. I get these 3 values. And so now I've got 6 terms that I need to add up, because it took 9 joules to bring in the second charge, then it took 23.1 to bring in the third, and then it took, what did that take? About 26 or so to bring in the last charge. And so when I add that all up, I get a total of about 58 joules of energy, positive energy. So I've done a positive amount of work. That means I've increased the energy of the system. And the easiest way to see that is if you release all 4 of those charges from their locations, right? Remove the pins, then those charges will repel and essentially go back to being infinitely far away from each other. Right? So I've increased the energy of the system by doing this work.